recap. So a protein is formed by stringing up amino acids in a chain. Chains are about 40 to 40,000 residues long. They form substructures, domains, in order to fold. But in principle, a protein chain put into solvent folds on its own. What is solvent? What's the native environment of a protein?
Water, aqueous?
Essentially water. It's a salty water solution, yes. And again, so they fold on their own and adopt a unique three-dimensional structure. The details of these structures are related to how they function. I told you that you can establish the similarity between two proteins by alignment methods. There's a sequence-sequence alignment method that compares pairs of sequences. And there's the next level of sequence profile alignment. In fact, it begins by building up pairwise alignments, sequence-sequence alignments. So this is my query sequence, and I build up a family of related proteins. From this family, I construct a profile. Profile essentially implies that I know what has to be conserved where, or what can be exchanged against what. And then I align this sequence against a profile. With that, I can recognize more distant relations in terms of sequences. And going one step further by profile alignments, I can even go further into what I call the twilight zones. So essentially more distant sequence relations that I can recognize the two proteins. Distant relations means I can recognize that two proteins that do not have similar sequences share a similar structure, or largely a main feature of a similar structure. I also talked about global and local alignments. Can you put that into perspective with a sequence profile? If I asked you, relate the words global alignment and local alignment to the terms sequence profile and profile, could you do that? I take it that not everybody is shouting I can. My suggestion to you is try to change that. So local alignments essentially are you align a local region, 50 residues, 50 consecutive residues. A global alignment is you try to establish that two proteins are aligned from begin to end, both. Okay? You don't allow any fragment overlaps. That's the difference between global and local. And global and local is true throughout all of these three different types of alignments. So for pairwise there's global local, for sequence profile there's pair, and mostly what we do really are local alignment methods. We can determine experimentally the 3D structures mostly by X-ray crystallography, and I may have forgotten to give you this image. So that is CERN in this ring. So the beam that you focus in this ring that is several kilometers in diameter, that is the beam that we actually use, that is actually used to get the structure of proteins. We at this point have about 120,000 in the database, in the PDB, the database of protein structures, in May 2017, and it's about $100,000 per protein. It's a little bit more than that for most of them. We can use computers to do comparative modeling. Comparative modeling essentially says we have two proteins of similar sequence. So that implies that they have a similar structure. If for one of the two, I know the three-dimensional structure for this template here, and this is visualized here. We have two overlapping proteins, two overlapping structures. In this particular case, of course, I know the structure for both of them. Just imagine, one of them I wouldn't know the structure. I could predict the structure for the other one because they're essentially very similar. And I do that by doing the sequence alignment. The sequence alignment implies what are the corresponding positions. That is the one for which I know the structure, and I read off at every point. So for the P, I take the coordinate of P in the PDB. For R, E, I take the coordinate of the I, and so forth and so on, right? You take the coordinate of this one for the query. And you pick always the coordinate of the corresponding residue. Okay, that's called comparative modeling. And comparative modeling, in fact, at this point can do over 40 million models. So at 100,000 per protein, this translates to roughly $4 trillion. That's more than GDP of France and England. So that's an immense amount of money that you essentially save by computers. The only way you can do comparative modeling, given is a very simple algorithm. but still it needs a lot of CPU time, and there are a lot of details to be fixed here. And it's an immense way to sort of save money. The bad news is that even for the sort of half of all the proteins for which I can do some comparative modeling, a large fraction of this protein I still cannot do comparative modeling. Okay, every other protein, every second protein I can sort of model some region, but not the entire protein. In fact, most residues, comparative modeling cannot do it. And for most residues, if we want to predict structure, we have to simplify or we have to get more humble, and all we can actually easily do is to predict in 1D. So there's a 3D structure, a 1D secondary structure, and that's what I'm going to talk about today. Secondary structure, I have told you, yeah?
A question on that 40 million thing. So if, maybe I'm missing something, but if we don't know the secondary structure of this 40 million,
yes,
how do we know we reliably predict?
Oh, so let me repeat the question for everybody else. Here I say, here on this slide I introduce, and in that lecture I introduced the idea of comparative modeling. So saying that you essentially can do that. If you have a protein of known structure that is similar in sequence, you can build a model. And we see here two proteins that have similar structures for which we could have done it. We didn't, because in this particular case we know the structure for both. Now on this slide I say we actually have 40 million models in the database, okay? And the question here was, how do we know, since we don't know the structure, how do we know that the models are right? Sorry, this is the slide I meant. 40 million models, how do we know that these 40 million models are right? And ultimately the answer is we don't. The way we convince ourselves that there is a certain level of accuracy is we pretend for protein pairs such as the one I had on this, got it in the wrong direction, such as this one. Assume I pretend that one of the two I don't know, okay, and then I build the model for the other one, and then I see how well do I do, and I see this, how well do I do, in correspondence to the level of sequence similarity I have. And then I believe that if I tomorrow will build a model for something for which I do not know the structure at the same level of sequence identity, I will roughly get the same percentage sequence identity. So you have to understand that since we have 100,000 proteins in the PDB, so if we sort of compare them with each other, we have a large database of things for which we can try whether that actually, for at least what we have today, is true. So there's an immense amount of empirical data that suggests how good these models are. They're not all right. We know that too. So in order to build 40 million, we have to build a lot of models that we know may be even wrong mostly. But we still hope there are important features in there about three-dimensional structures from which we can learn to do better experiments. And again, there are models where the sequence is very similar that are most likely very right, at least where they are built. And now we get into secondary structure. When we look at three-dimensional structures, we always see substructures, macroscopically visible elements, secondary structure. We see these alpha helices, and we see these beta strands, two strands form through hydrogen bonds, a sheet. And in the alpha helix, again, the bonding pattern is I and I plus 4. Okay, so that brings us to this statement. Science really is communication. It's very important that the phase of your master study is the easiest for you to realize this reality and learn it. Communicate. It is about, well, the weather or whatever, but also about what you do. This is the way to learn it. Okay, communication begins with questions. Are there any other questions? Again, we are beginning to sort of get into the major phase of what I believe is the most important part of the lecture, and maybe from next week, again Tuesday there will not be lecture, but next Thursday on I will stop in at least a quarter of an hour before the end of the lecture and begin to sample questions. So here's another story that has nothing to do with this lecture. It's a company looking for people who want to do a master thesis or just have a heavy job or something like that. And the background of this company here is essentially they're trying to do image recognition. So the idea is you, for instance, have a problem with your arm. And the problem with your arm could be that you had an injury and you need physical therapy. Or the problem with your arm is you want a big muscle and you don't have it. And you stand in front of a mirror and you see yourself in this mirror, and then the mirror will show you how you have to do physical exercise in the most optimal way. So how do you have to lift some weight, or how you have to move the arm so that you learn to become mobile again. And that is what this startup company here is trying to do. If you want to participate in that, I believe it's a very cool project. Okay, so now we get into secondary structure prediction. The first one is about words. So there's secondary structure, there's 2D structure, and 2D structure comes from this idea of secondary, 2D. For some people, when they see the word two, they think about all kinds of things. Anyway, so this is all nonsense. What is reality is this is 3D because there are 3D coordinates, very clear, very well defined. You need 3 vectors to span a point in this space. 2D is contacts, distance maps, and is also very well defined. There's a 2-dimensional information. I told you that the information content here is less than 3D, obviously, but nevertheless, this contains, except for the mirror image, all the information. So you can reconstruct the 3D structure from the full distance map. 1D, just a string, and the string is 1D. There's nothing 2D about it. It has no contacts, right? Yes, secondary structure is formed by hydrogen bonds, but the moment you write it down, and that's actually what we're trying to predict. We're trying to predict which residue is in a beta strand or alpha helix. And at that very point, it's 1D information. And again, there's a method that uses 3-dimensional coordinates, DSSP, to infer secondary structure. Essentially read it off the 3-dimensional coordinates, and it does it by finding the hydrogen bonds and recognizes some patterns. So there are helices, 3 types of helices. That's not important. Essentially, the 3-letter alphabet in some sense is there are helices, there is the extended structure, which is the strand forming sheets, and there's everything else that is not well defined. Now, when the authors of DSSP applied this first objective method to assign secondary structure to 3D structures, they found that some sequence stretches are always found in some particular secondary structure. So this was always found in a helix. This was always found in a beta strand. This was always in a loop. And then there were pentapeptides, so 5 mers, k mers of k equal 5, that were found both in helix and beta strand. Now, how can that be? How can you have the same 5 residues, sometimes in a beta strand and sometimes in a helix? Any idea? Yeah? It depends on the environment, exactly. So it may be that these 5 sit next to something that makes them form a beta strand, and if they don't sit to that makes them form a sheet. Then they do look like a helix, for instance, right? You could imagine that, and that is exactly what happens. This is the idea shown here. Clearly, the helix is more local than the sheet. Now, and I believe I put that slide in the wrong place. A simple method to predict secondary structure, the simplest method, would essentially be exactly what I showed before. Take all of these runs that are unique to some particular class. Whenever now in your new protein, you find this run of letters that correspond to a particular secondary structure, helix, strand, or other. In the 5 mers that are in both, you don't take. You only take unique ones. Then you have a secondary structure. Okay? The problem with that, obviously, is you may, for the sequence that you predict the secondary structure for, not have all these elements that are there in the database. So some may be new. So you may not be able to do that. And they may also have conflict situations, like this 5 mers that are in 2 different states. But the first secondary structure prediction method that was there was actually much simpler, and it comes from somebody, Szent György, Hungarian, who also got a Nobel Prize. Not for this secondary structure prediction method. That was in 1957. And essentially what Szent György said, well, you know, looking at the chemical with the way the chemical structure, so the way amino acids look, and what I show here is 20 amino acids. There's a particular amino acid here that forms a ring called proline P. And the proline, since it forms a ring, it bends the main chain. And if it bends the main chain, maybe this is the kind of thing that stops a helix. Because when you go out of a helix, you go in the helix and then suddenly you change, right? So you need something such as a proline, was the argument here, to make that happen. To go from a regular way of attaching amino acids to getting out of that loop. And so essentially he predicted that prolines would break a helix, meaning that whenever you see a proline, that's the end of a helix. That was the first secondary structure prediction. Now, essentially, we talked about that briefly, going from proline breaks a helix to an odds ratio or some probability for all 20 amino acids. It's very simple. You just build you take a large database from DSSP, you take from the known structures from PDB 100,000, you filter out things that are biased, and then you begin the count of this table here, and essentially you get a probability matrix. Okay, now here's another story. I talked about it on Tuesday, about bias reduction, redundancy reduction. I said that if I just looked, PBD is about 120,000 chains, and if I just asked how many are there that have less than 100% sequence identities, or put it differently, how many of these 120,000 are identical to something else that is in the PDB? And then I said it's about half of them. So about 60,000 identical to something else, and I argued this is because, one, you have separate experiments testing different binding sites. Two, you have different groups getting the same solutions because they compete. Three, some groups don't really compete, they do it years later and get a higher resolution, higher quality structure. So there are different reasons why you have these things in there, and you should filter them out. But okay, this is very clear at 100%. Now should I filter out at 99% or 97%? Where should I put the line? Where do I stop filtering? What is bias? And the answer to that question is intuitively very clear. What we want to do here is get a probability table that reflects the proteins that I will predict for. Okay? The proteins that I will predict for are all those I cannot reach by comparative modeling. So they're out of the reach of comparative modeling. So that's what I know. In this universe that I want to represent, so I built the probabilities from a data set that has to be representative for the world that I will use tomorrow. That's the idea, right? That's unbiased. It represents what I need tomorrow. And that is exactly the constraint here. The reason why we do this bias reduction after, so at the first step, 100 is clear why we do it. And after that, the next line is really, what am I going to apply my method for? It has to reflect what I will apply it for tomorrow. And that essentially means outside of the comparative modeling range. Anyway, so this simple odds for all, the simple idea here, there's a bunch of methods that did it. Chow-Fussman is after the two authors. And then GOR is a method that originally was started by Barry Robson. And the acronym here comes from Garnier, from their last names, Osgothorpe and Robson, the three. Garnier was the biologist and Robson was the mathematician or the algorithmic person behind it. And essentially this is exactly it. So you look at particular secondary structure and you say that the probability of forming a particular secondary structure depends only on the amino acid identity, implying that at two different positions the same amino acid will have the same probability to form this secondary structure. Now, where do we get the secondary structure from? I already said this is essentially from DSSP. There's this resource from PDB, and over the years it grows very, very much. By the way, so when these first methods were done here, Gore and Chow-Fussman, we are at a point where we barely had 100 structures in the database. By the way, there is something called the molecule of the month, and sometimes there are interesting stories about what we can learn from 3D structures. So just looking at it is possibly interesting. So then find a unique subset, convert 3D to a secondary structure with DSSP, and do the prediction. And ultimately, I don't know why I have the same slides in again. That gives us the first, what I call the first generation method, Chow-Fasman, GOR, methods like that. Essentially, a simple probability. Now, the next problem is, of course, how well do these methods do? So how do I measure accuracy? And an example is here. I assume, so the sequence is running, the numbers here, the number of residues, so residue 1, 2, 10, 20, and so forth. This up here is the observed secondary structure. Blue means that there's an strand. So empty, blank means there is the loop or the other state. The second line, PRD, is predicted. So the red one here means the helix is predicted, here too, and here as well. So how do I measure accuracy? How do I measure performance? How good is the secondary structure prediction that I have here? Throw some ideally somebody from the Rost behind, so that I don't have to repeat the question. It's simple. Just give me some way of measuring it, yeah? Not quite behind, but...
Maybe simply, you have 100 observed ones, and you know 100 observed structures, and maybe 50 are, 100 are the predicted ones, and 200 are the observed ones. And so we take a difference. If it's smaller, then you know your predicted structures are much closer to the observed ones, if not.
Yes, you're totally right, and I'm not going to repeat it. I hope that everybody heard it. But the other reason why I'm not repeating it, I want more detail. Yes, you take the difference. I have two strings there. How can I do the difference? So what's the simplest thing? I'm not going to. I'm ignoring. I'm sorry. I'm ignoring the first rows here. Sorry, gentlemen. Thanks for being there. Somebody up there? Come on, you're a computer scientist. What's the simplest thing? Yeah. Yeah, you can count mispredicted. So is that what you said? So that is an interesting answer, because it's a particular choice that I, in fact, personally did not expect from this group, from you as computer scientists. But the first statement here is, I simply count where I'm wrong. And 1 minus that, of course, is the count where I'm right. And that is what I sort of expected, which essentially is the edit distance, right? But 1 minus this solution is the edit distance, so it's exactly the same story. You do see, however, you immediately, this answer here is one that answers it on every single residue. It's an edit distance. You could also perceive this as segments. So you could also perceive this as there's a helix, there's a beta strand, and you have to get the entire segment, right? This is not measured here. The edit distance will also not tell you whether you're going to be better on helices or beta strands or loops, or the state other. On my slides I call it L, but I will refer to it as other, or the blank state here. So the edit distance doesn't distinguish, right? And you immediately see there are different ways of doing that. But the edit distance is referred to in the field as Q3, essentially number of, this is exactly the edit distance, and it's called Q3 because it's a 3-state accuracy, if you want, right? Okay, in terms of 3-state accuracy, these first generation methods, they get about 63%. Okay, so the first question to you, is that a high number? So 63 is higher than 0. Let's not observe this simply, yeah?
It's also better than random.
It's also better than random. What is random?
32% if you have two states.
So if they're equally distributed with 33, they're actually not equally distributed, so it's going to be 35 or something like that. So it's clearly above random. Okay. Now what we found out, or what the authors of DSSP found out when they measured, or we found out over time, is that clearly was an overestimate. So performance is more in the ballpark of 50, maybe 55%, okay? Which is still clearly better than random. But it sort of dropped, so the 50% is much closer to 35 than the 65 number, or 60 number, 63 number that was initially published. Okay, now this I call the first generation method. So there's going to be a second generation method. What are they going to use? Some of you may remember that from Tuesday. What's sort of the step up? First generation uses an individual amino acid propensity.
Also assign a probability,
Yes, we could assign a probability for rather than individual amino acids. Yeah?
Sliding window.
We could have a sliding window, so we could have adjacent information. We could integrate somehow information from a stretch, from a local area. So rather than just looking at the V's here, I would look at the entire string of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 residues here, shown in green. And we would somehow not only see that there's a V, but it's the V that is in the window of 11 with 2 other V's and some other residues. And this is the idea of a method that is referred to as GOR3. Again, Garnier, Oscathorpe, and Robson, but the publications include other people, which reaches a level of 55 to 60% edit distance, or Q3. And again, so essentially what you do is you compile a conditional probability for the center in the window conditioned upon the other 20 residues, which of the other residues is at position -1, -2, -3, -4, in this -1, 2, 3, +1, 2, 3. So this is a window of 7 consecutive residues that are shown in the red here. And that's essentially what you compile in this probability. And so the idea is very simple. Working out the probability in detail is highly non-trivial, and that's the achievement of Barry Robson here, to have introduced that for the first time. The problems with these methods of the second generation, well, the first problem obviously is it's not 100%. That brings me to the next question. Well, we know that the worst you should at least beat random. You should be better than random if you want to have a good method, right? But is 100% what you really, is 100% the number of what you really expect to get? And on Tuesday, there was an idea that would question this. I'm not sure whether the person who brought up the idea, who it was. And I'm not sure that from this sort of way I'm saying that you recognize which idea I'm talking about. Obviously you don't. So what is the ceiling? The bottom should be random. What's the ceiling? Let's not talk about what is on the whiteboard. On the whiteboard you see the number 65, they say. I'll get back to that in a minute. But I'm talking about a different ceiling. I believe you said it. I attribute the ceiling to you. So can you fill it in?
The agreement we can get well-to-manual annotations of the secondary structure.
That's an interesting idea, and maybe that's also what he actually meant last time on Tuesday. This is not quite what I meant. So he said, and that's a very, very good one. So the ceiling would be if I had 2 experts or 2 algorithms assign secondary structure from the same 3-dimensional coordinates, and they disagree slightly, then your prediction method will never do better than that. That is indeed one way of defining the ceiling. Another way of defining the ceiling is there is a little bit of motion in the structure that has to do with function, and you do the same 3-dimensional structure 5 times and you get slightly different secondary structure. That variation you will never capture, because it's intrinsic secondary structure can slightly change. There are regions where it will not change at all, and that is important for function. Which ones, bless you, which ones it will change, it will not change. But this clearly is one way to define the upper end, and it's not 100%. In fact, I'm not sure I will ever get to that. That is more in the ballpark of 90%. But here's a different story. What I say on this slide here is, they said in those days, methods cannot be 100%, the limit is 65, and the argument was that essentially when we look at a window of consecutive residues, we do not see all the global information. Helix forms by local interactions, but not strands. And in fact, when we look at how well, so if we don't use the edit distance, but if we ask what's the accuracy in predicting, or how many errors do you make for predicting strands, then the answer is 40%. So strands are predicted at a level of 40% accuracy. Now we are at a level that is very close to random. In fact, some methods predict, as a fact, some methods predict strands less accurately than a random prediction would do. So again, the argument was that the formation of beta sheets is absolutely not local, it's sequence. So when you cut out here and shown 7 consecutive residues, the beta strand hydrogen bond here is formed to something that is way further away than 7 residues. So when you look at a 7 residue or the 5 residue window, you see the 2 binding partners in an alpha helix. I and I+4 is a hydrogen bond binding partner in the alpha helix. The window of 5 has both of them in. In a beta strand, the binding partner is far away in sequence. Will not be in the window of 5, will not be in the window of 11. In many cases, will not be in the window of 21. Yes?
In this particular case of this protein, there should have been like one strand of E's, then a long loop, then E's again, then short loop, then E's again. So between E's, there are some nothing regions, right?
Yes.
And this blue and white, they are like not strands and not helices.
Yeah.
There's something else.
Yes.
So this is not one continuous strand. This is part of strand, then it gets
Yes. Okay, let me repeat this, because I had not seen that this could be a problem. So the blue-white is the chain, and the chain essentially, let me see how it runs. It begins here. My pointer is somehow, it's not the battery, I don't know why. So I'm just gonna it did, darn, it's not the battery. So you see that it begins here, then it goes into this yellow arrow, it goes up here into the blue, goes into this arrow, goes down, behind, and then back here, and then out. Right? And between these yellow arrows, those are the strands, the yellow arrows. The black arrows here indicate the hydrogen bonds. And in between, there's none E. So what is white in the white and blue regions here in the structure are something that is neither E nor H. So it's L or O, is other, right? Okay. So beta strand formation is not local in sequence.
Can we maybe not take longer amino sequences? And
Yes, we can take longer sequences, but the way I already, so when you go, this is the beginning of the protein, and this is the end of the protein. So this could be a protein of 50 residues, and if you take longer ones, well, yeah, okay, if the window is 50 residues long, now some proteins are 100 residues. Okay, if the window is 100 residues long, oh, now you get a new problem. The new problem is that some proteins are shorter than the window that you have. So, yes, we can try to increase the window size, and I'll get back to that point. To some extent, this is what people tried and somehow didn't work, and I'll get back to that. But the argument simply was, clearly, the helix is more local than the beta strand, and maybe that is the reason why beta strand is predicted less accurately. And maybe that is also the reason why 65 is the upper limit. So the reason why people said 65 is because people tried almost any algorithm by the mid-90s to apply to this problem, and none of these methods ever got above 65. In fact, we know today that none of them ever got above 60. Just they made some measuring mistakes. Let's not dwell on this. But essentially, they argued there must be a ceiling. We do know that there are global interactions, and we don't know how to put them into the system. So therefore, the types of methods, they said, is constrained to 65%. There was an additional problem, the problem of short segments. Let me illustrate that. So a typical prediction, so again, that's the observation up here, the blue. In black above you have the sequence. A typical prediction would be the one down here. And what you see is that, I'm just trying to wiggle a little bit with the batteries. I believe this is really a new pointer. So you see there's an E, and then there are 4 residues of H. Then there are E, here's H and E. The point is that all of these predicted helices and strands are so short that you don't know, does it mean that this is a long helix? And I should just remove these E's. The same here, is this a long helix? This is a very short one. Should I just remove the whole thing? Is this a long E? So using this is difficult because you don't know what it means. What you do know is there's no helix of 2 residues. So that cannot be true. You just don't quite know how to make the best out of that prediction in order to make it look more realistic. And at this point, I'd like to insert again what I talked about last time briefly, the concept of neural networks, machine learning. Again, we have an input here, we have connections, we multiply these 2 vectors, have the dot product, define some sigmoid function or hyperbolical tangents, and after this hyperbolic tangents, you have the output from this unit here, and the type of problem that you can solve. So you may not see that. This is an open circle, this is a dark circle. So this would be the input 1 and 0. And for the mistake essentially that the method makes is simply the square of what you have from what you want. And training it means the only thing you can change are the connections. You train by essentially going downhill. In this example here, in the first training, so if that were, if you typically you initialize the junctions with random values. I just have put 1s in here for simplicity. So if they were all 1, you see, so, okay, let me go one step back. So 1 times 1 is 1. Plus 0 is still 1, but the point is you want a 0 here. Okay? So you have to decrease that unit, that connection. So say we flip it here to 0. And the other one, we have to increase both because here we want to signal a 1 as an output, right? So we increase these 2. So in the next step here, we see that we have to decrease this further, and so forth and so on. So you step by step change these connections such that the error is reduced. And with that, what you essentially do is you introduce lines to separate the points. Now, for this problem on the left-hand side, all the lines that I show in terms of the neural network would be equally good. For an SVM, there's a clear solution, the one that is getting the highest distance from all the points, meaning that most likely this line here for an SVM would be the best one. For a neural network, there's absolutely no difference between these lines. They all solve the problem. So in terms of the error function, you make a mistake or not, none of them makes a mistake, okay? This problem here, we cannot separate with a single straight line. We could separate it with a non-straight line, or we could separate it with 2 straight lines. And in the language of the neural network, the introduction of a second line, essentially the introduction of a hidden layer. The math between the layers, between the units is essentially the same. Again, you would do this error function, you do the decision function, you do the nonlinear decision, you have an output, you have an error, and you go down in the error function. This is the downhill movement that I talked about. You go by a step, width of epsilon, according to the error that you make. Then the next term here, the alpha, brings in the change from the time before that allows slight uphill moves. Depending on how high you choose this alpha to be, the uphill move is is higher or lower. Now, typically when you begin with these neural networks, when you do it for the first time, you choose an epsilon that is high, something in the ballpark of 1, because you just want to find out how the system works. When you do know that you can do the problem that you have, you lower that by a factor of 100. And typically the alpha is sort of a factor of 5 over the epsilon, but you do it very, very, very slowly. When you do it very slowly, you're most likely to find the most optimal point for the prediction. There is, what I show here is training time. What I show here is accuracy. So 100% is completely correct solution. And I have two lines. Can anybody guess what these 2 lines stand for? And what this arrow, the gray arrow here stands for? Yeah?
The arrow on the training set and arrow on general.
So, training set you said for this one, is that right?
For
The brown, I believe it's actually green. Yeah, it's green. I know it's green. I changed it yesterday. So the green one is the training set, and the blue one is?
Yeah, maybe the training line fits very well to the training set, but for predictions it's not so good.
So the blue you call the prediction set, exactly. And this then it works very well, or doesn't work very well. Typically we call that overtraining. So meaning that yes, you can learn the problem. The green goes up close to 100. But when you learn to do it close to 100%, then what you learn is relevant only for your training set. It's no longer valid for your prediction, as this was said, or as often called the testing set or the validation set. There are many words out there. Essentially, it doesn't work for problems that you will do tomorrow. Okay? That's the idea. And that's overtraining, learning by heart, or whatever you call that. Okay? Fact is, this is a toy problem. This is what you get in every lecture on machine learning. That's the idea that is governing, and I'm going to show you real data in a moment. You already know, so this is cross-training. Let me repeat this, briefly introduce for the first time this idea of cross-validation. So the pi is the entire data that you have, entire experimental data. So for DSSP, you would have 120,000 structures. You would redundancy reduce, maybe get to 10,000 somehow sequence unique structures. And for these 10,000 proteins 400 residues long, 10,000 times 400, 4 million residues in secondary structure, that would be the pi. Okay? And then you separate this pi, and you take some out for training, in green here, some for cross-training, and I'll get back to what that means later, and some for testing. That's the blue I showed you. And a real case for secondary structure prediction method, the testing in blue is here. Yes, you can train. The green one does go up, but as you can observe, in the real case, it is nothing like this clear overtraining effect. In fact, it's very unclear where you put. So if you put the first time it goes down, then overtraining starts here, right? If you sort of went for a local maximum, then overtraining starts here. It is not that easy to see. And this, in fact, in real problems, is the real problem how to stop. And that ultimately brings us to the cross-training story. Let's get back to secondary structure prediction. So now we can essentially use this machine learning device and predict secondary structure. Rather than using the tables, the conditional probability, we can just look at a consecutive window of 11, for instance, 11 consecutive residues, and put that into the machine learning device and hope that we will solve these major problems, that we will get closer to 100%, that we will do better on beta strands, and that we will have longer segments. The way to do that now is, this is the input. What I show here is 13 consecutive residues. So I cut out 13 consecutive residues. In this particular case, the P here is at the center of this window of 13. So it's plus and minus 6 above, 6 residues before, 6 residues afterwards. And every one of these yellow blurbs here essentially stands for the 20 different amino acids. So every one of these blurbs has 20 input units, and actually not 20 by 21 for the spacer. Can anybody remember why we need a spacer? Or what the spacer unit is for?
Bias.
Bias?
Because you have beginning and then.
That's the point. So when again, I'm going to explain it not with 13 as on the whiteboard, but I'm going to explain it with my 5 fingers. If my center finger here is going to be the one to be predicted, and now if this center finger is the first residue, then the ones above it are not amino acids. There's something else, right? And that is what we need the 21st unit for. So the input space here is 13 times 21. Okay? The output is very clear. HEL, helix strand other. And in between I have the hidden units. Okay. Yeah? Can you try a little bit louder? Oh, why 13, not 11, not... so the first solution, let's begin, why do I not take 1? 1 would be the first generation method. That is not good. We want longer windows because we know that consecutive information is relevant. So when I first did this, the number 13 essentially came out of the reality that my data set was so small that I couldn't take very large numbers. But I could do 13, and I could do 11, and I could do 15. And I tried them. And 13 turned out to be best. That's the simple answer. Later, when I read it, that many years later, in fact, this first method that I did was called PhD. And later there was a method called Prof, and somehow you can sort of imagine why this name changed in my career. Anyway, so for Prof, this number moved up to 21. So because I simply had more data, and more data then was good enough for longer windows. Because it worked is the simple answer, yes?
You said each of them is 21, so this is one hot. Okay.
Say again?
This is one hot, each of this 13 is one hot vector.
Yes. So each one of these blurbs is 21 input units. So in this particular case, it's 13 times 21 input units. And as I just said, for a later version, it was 21 times 21 input units. Actually, even more complicated. I'll get to that in a moment. So, what do you believe? Did the machine learning do better? I can tell you that I worked on this for quite some time, and I was sure this would have worked. Okay, it was many years ago. I was convinced it would work, and absolutely didn't. So my conclusion, so the overall accuracy, this edit distance here, the Q3 is 62%. So 62% of the residues were correctly predicted in either helix strand or other. It was slightly better than other things, but not really. So my conclusion from that story was that if, as a developer, you believe that you just apply a fancy algorithm, a fancy new method, even if you are one of the few who can do that at that very moment, that still doesn't bring you anywhere. You have to do a little bit more. But if you understand your method that you apply, maybe you can get you can get a few additional yards. And one thing that I looked at was this one here. I call it the training dynamics. So what I mean is, on the x-axis I show training time. So I present my samples. So one step here means I present every single training example exactly once to the system. Okay? Every single time I present a sample, I make a downhill move in my derivative of the error with respect to the connections. So this is 20,000 changes, or whatever database size. In those days it was about 20,000. 40,000, and so forth and so on. And I show here how well I do for 3 secondary structure states. In red is the helix, and blue is the beta strands, and in green is the other. Okay, what do you observe?
Strands are simplified.
So strand blue is the lowest. True. Something else. What else do you observe? They don't, say it again. They don't change much. That I would contest. So blue does change. They saturate. You mean? Yes, so that's the second observation. We have sort of it looks as if at some point we have a saturation, and after this point of saturation, what you essentially have is a constant sum over the three. So the red goes up, the green goes down. The only exception to that is that the blue goes up a little bit. Keeps going up a little bit, but then also reaches a point of saturation. But let's just go back here. In the first step, before this graph essentially starts, or when this graph starts, I'd like to point you to the fact that the blue is very low, and actually the blue goes up from that point substantially and stays up. Yes, it iterates, but it does not stay at the point at which it's after the 20,000, while in fact green and red are never moving much from what they did after the first, right? So from the scale here is from 1 to 10. So 90% of the time, in some sense I can follow what you said, 90% of the time actually nothing happens except for strand. Most of what has happened for the other two has happened in the less than 10% that I'm not showing on this graph. That is before the 1. Okay? Okay, now why could that be? What could have caused that?
Maybe it's relatively easy to predict the first two, and that's why the network learns it rather quickly and then cannot do much better. So
the statement here is helix other is easy, strand is difficult. That's why it takes more time to learn strand. This is in principle the right answer, but you have to sort of go do another step somehow to turn this answer into something that you can actually use to improve.
Isn't the drop seem the opposite? Like performance is 1 in the fourth, but the strands, okay, for strand it's 0 and for helix it's 1. No, I was saying maybe the graph is reversed.
I did not understand what you said, but you understood now, or what?
Yeah, no.
Good.
The performance, I was understanding the performance axis here wrongly.
But again, so the point is that yes, strand is most difficult to learn. Why?
maybe it depends on the others.
Maybe it depends on the others?
Other helix. So after you learn about the other helix, maybe you can learn about strands.
So that's the move in the right direction. So maybe you first have to learn the simple truth about helix and strand, helix and other, and then you have time to sort of learn more about the complication of strand. That could be. How could we test that? So, by the way, let me point one thing out here. You said it in a way that is slightly misleading. You're actually right, and this is misleading. Would you have said it wrong, would have been much easier to learn from it. Some people immediately said, well, this is because strand is difficult, because strand is non-local. Remember, strand is predicted at random probability. But it is true that strand goes up. Right? It's not that, well, yes, the blue is always, that his observation was observation number 1 here. Blue is always below the other ones. Blue is worse, that is true, but there is something it can learn about strand. It just does not start with it because maybe it has to learn the others first. Maybe it takes more time because it's more complicated. How could we check? Well, or what could that be related to? It could be a tough problem, but I'm showing you something else here. The pi that I show you is the fraction in the correctly predicted residues. So the whole pi is all the residues that are correctly predicted. 62% is the Q3. So the pi is the 62% of my data set that I correctly predict, okay? And now I'm asking, for the 62% that I correctly predict, for all those residues that I correctly predict, what fraction of those is helix, red? What fraction is beta strand, blue? And what fraction is other, in white? Okay, the white may not have been the best choice here. But you clearly see the red and the blue. And you see that, in fact, the white is the largest. and that the red is the second largest and the blue is the smallest. When we look at the distribution in the database, that's what you see on the left. Does that help somebody to sort of formulate our next step, what we should try?
Maybe we should have a look at the a priori probabilities of these structures appearing in our data.
A priori probability, you mean essentially look at the probability table that I talked about before, or the distribution?
Yeah.
The distribution is this one. So this is just the fraction of helix in the database, which is the simplest way of calling it a priori probability, right? That's, for an HMM, this is what your first prior would be. What fraction in my database is helix? And that is exactly that.
So what I mean is maybe we should try to build our training data set in a way that it equally reflects these things.
So the point is here, we should build our training set. So this is essentially the prior, the database distribution, that if you randomly, for anything, independent of amino acids, would predict alpha helix, you would just take the database distribution, right? Now, what if we tried to put into the system an equal distribution, shown schematically here on the right? How do we do that for the neural network? Well, essentially what we do is we sort of, at every single training step, we present one example from helix, one example from strand, and one example from other. Which ultimately at the end of the day means we oversample strand. We oversample the smallest, oversample in the sense we sample it more than it's actually in the database. But we sample all three classes equally. Since they're not equally distributed, we oversample the ones that is least distributed, right? The language is clear to you. So this is typically we present one sample at a time, and what we now should do is we should sum over three, so over one from each class. Idea is clear, is it? Good. When we do that, so here's again what we get for the regular way of doing it, and here's what we get for equal sampling. Yeah?
So what the data is sufficient on strands?
So the question is that because we didn't have enough strand? So on the left, what is the answer to that? Yes, absolutely. I don't even have to bring in new information. I can just resample the same information I have, and I get something that is absolutely the same. So the red one is somewhere behind here. Sorry for the plot, but the red one is just exactly behind the blue. It's not my mistake that this is the case. But you see that essentially those three lines now from begin to end are similar. Okay? Yeah?
Just to understand the process, right? This is like batch training on very small batches of three where you pick your elements of the batch being distinctive.
Okay, so what we have here, the way the neural network is trained is what is typically referred to as a batch training, meaning you present every single example and you choose the examples randomly at a time. And then you do tiny epsilon moves, okay, every single time. And now the difference between the one on the left here and the one on the right is that on the left I take them absolutely randomly, which means I take them in the proportion of the occurrence of helix. So about half or a little less than half of my residues are other, class other. So about half of the time I will pick other, residues from other. While on the right hand side I will pick them at equal probability, because I will pick a batch of three, a micro batch of three. Yes?
But the problem in that sense then not that there are too few stars, rather the ratio is quite.
Exactly. So the network simply could not learn strand because it was occupied. So you had suspected that it would be occupied, and that would be in the way that it had to learn the others before. And if they are sort of in a statistic distributed in a statistic way, it will learn it at the same speed. Yes.
Does the accuracy change after balance training?
We get to that in a moment. Okay? So does the accuracy change, is the question here? Yes, it does. Unfortunately, it does change in a different direction than I had wanted. So it goes down. And this happens simply because what we now do, what the balanced network here does, it does better on the minority class. The number that I measure here is the edit distance for everything, but does not distinguish between minority or majority class. In fact, that number is mostly influenced by the majority class. So if I develop a method that is best for the minority class, this number will go down. Right? That may not be quite what we wanted, but clearly we have something in terms of the accuracy of beta strand prediction is exactly the same for beta strand, helix, and other. All classes are predicted at the same level of accuracy. So this pi is actually an exact 3 split. So the conclusion from this exercise here is that the neural network does improve if you know what you're doing. It clearly does do strands better than random, and in fact the statement that strands are not predicted correctly because we have such a local window is just wrong. It makes a lot of sense. Yes, it's true. Beta strand formation is not local, but I can use local information and still get the same prediction accuracy. So the propensity that I have in the sequence alone is good enough for that. And the conclusion from that is, sometimes an explanation sounds very, very reasonable, could still be wrong. And this one was wrong. You could prove it wrong. So let's get back to the other issue of short segments. So an example of what I mean by short segments I showed you before. And essentially, when we look at observed helices, there are about 10 residues. That's indicated on average here. This is indicated by this one. Beta strands on average 5 residues. And what is predicted is on average here. So it's about half the length of what you want. How did that happen? Well, ultimately the way it happened is that the network that I have so far has been trained on randomly selecting points. So what you do is you put all your 10,000 proteins into a database, 4 million residues. Each residue has a secondary structure assigned to it, and now you randomly pick from this database. Okay? Now, randomly picking from the database means that you will not pick I plus 1, I plus 2, I plus 3, I plus 4. So the network will never see that there's a correlation between adjacent residues. It will pick in the database sample 42 and 42,000 as a next step or something like that, right? And it has to be so, because otherwise you're more likely to get trapped at minima. And you will somehow lose these local correlations. How could you get these local correlations in to the system? What could you do? Again, you cannot change your sampling. You cannot keep choosing in deep learning. So in deep learning, this is what people do when they do image processing. They introduce correlations that are wanted because you sort of want to see what is in one image, and you do use that at subsequent time steps. And there's a good reason for that. But in this context here, this would lead in the wrong way. So what could we do? How could we bring in correlation? How could we bring in that a helix has to have a minimal length? We discussed on Tuesday that we could sort of enforce upon the prediction method in the end that helices have to have a certain length. And we discussed also that this would lead to a set of rules that are not easy to formulate. Can we teach? We have a machine learning device. Can we teach it to learn this? How could we do that?
Introduce a hidden layer in order to constrain this minimum or...
This is essentially have you done deep learning? This is essentially the way deep learners would do this. So they would introduce another hidden layer, and that other hidden layer would have some local structure that would essentially constrain my prediction to increase the probability of doing this. This is one way of doing it. Here is a much simpler way of doing it. You sort of combine final systems, let's call it like that. It's sort of somehow similar to deep learning, but it's not in one system, it's sort of separated system. So here's what it is. This is what I showed you before. So I have 13 times 21 input, hidden, and 3 output units. So it's a device that takes sequence as input and predicts secondary structure. Okay? And it has 3 output units for the 3 secondary structure states. Now what I do is I sort of take 3 of these predictions. In this particular case, so I have a window of 3 shown here. So that's for residue I plus 1, I plus 2. So I is in the middle here, I plus 1 is in the middle here, I plus 2 is in the middle of this one here. And I get 3 different, for 3 consecutive residues, I get 3 secondary structure predictions. Now, what the red one here is 4, because again I need a spacer, just like for the 21 amino, or 20 aminos plus 1, I need a spacer here too. So this is going to be the input. What the first level predicts is going to be the input for the second level. And the second level then is going to have a hidden layer and an output layer. So in contrast to what we do today in deep learning, these are separately trained devices. And deep learning, what you would do is you would essentially not really have an output, but you would, the idea that you formulated is you essentially would put this directly connecting into the, you would connect essentially the blue ones, okay? The advantage of this one here is you sort of have fixed devices that you have easier control over. And then you can redo this. The result of that is, on the second level, that essentially the predicted secondary structure looks very much, on average at least, like the observed ones. So these are the averages here, first and second level. So this is the second level predicted, observed, predicted, observed is very similar. And here, in more detail, you can follow there this distribution. Now, a remarkable story here is, this was an idea that came to me. And I thought I had invented it. Interestingly enough, somebody else had published it before me. So I published this in '93. Somebody else had published the same method in '88. And that was in fact the first method, Chanchanovsky, the first method that applied neural networks to predicting secondary structure. The point was that they tried to use it in order to improve performance. It didn't work. It didn't improve performance at all. So they, in their paper, wrote that the Q3 hardly changes, and somehow that sort of de-emphasized this solution because it didn't work. They never thought to apply this to learn length or to learn relations of length. They never looked what it really changed. So who invented it is difficult to say. Anyway, it had, so sometimes when you get something out, you have to see whether it improves in many different ways. Okay, there are other ideas in which you could have done that. So one is you, rather than having 3 output units, you sort of have longer output windows, for instance 9, so 3 consecutive output, or 3 consecutive residues output. This somehow works. It did not quite work when it was first done, but it worked later when there was more data. But then the other idea, and that really worked, is feed-forward or recurrent neural networks, coming from Paolo Frasconi initially, and then worked out by Gianluca Polastri and Pierre Baldi for secondary structure prediction. So in this particular case, the output from one level is put back into the other level. So it's, again, this is not deep learning where we connect the levels directly. It's where we connect particular parts of the network back as input, recurrent networks. But the other problem is all of these devices. So we solved the alpha helix or the beta strand problem. We solved the short segment problem, but accuracy is still only 60 plus something percent. How can we get it up? How can we move up from the 60%? How can we put more information into the window? And I believe I'm gonna somehow leave it at the question mark. Give you the